So the next speaker is Konstantin Lukin, Professor Konstantin Lukin. He is a guest professor with ITA at the moment. He's from. Maybe you can introduce yourself a little bit when you start talking. He will talk about the method of side lobe suppression that he worked on with colleagues from Unicamp while he was a guest professor there. Yeah, Konstantin, the floor is yours. Please start.
Okay, thank you very much, Felix, for this kind introduction. And first of all, I would like to thank the Institute of Technology Aeronautica and personally Renata Machado and Felix Eintracht for giving me a possibility to make research in working on this project. And today I will, I came to Brazil 2 years ago for the FAPES project, and my permanent working place is Institute for Radio Physics and Electronics at Ukrainian Academy of Sciences in Kharkiv city, but now there is a war. That's why I got the possibility to continue my research in Brazil, in Campinas, and now South Zeta campus. My main field is noise radar technology, but also working with antenna and synthetic aperture radar, ground-based synthetic aperture radar. And here we worked on SAR imaging or even SAR tomography in drone-borne synthetic aperture radar. And the title of the project is Method for Suppression of Angular Side Lobes in Drone-Borne SAR Tomography. The work was started when I have been working in Campinas with Unicampi with my colleagues Juliana Goes, João Roberto Moreira, and Hugo Enrique Hernandez Figueroa, who is now the Dean of Electrical Engineering Faculty. Very brief introduction that synthetic aperture radars tomography is in a wide use in radio frequency and microwave ranges. After its implementation in a drone-borne platform, this technology drawn extremely high interest related to the multiple civilian and military applications. For example, the drone-borne multiband differential interferometry SAR and the obtained with its help results presented in the cited works in Campinas by Moreira with colleagues, João Moreira with colleagues, and also I apologize, Laila Moreira. The company Radas and people from that company and also from the university. And they experimentally have shown that the 3D SAR imaging and even SAR tomography is available or specifically when applying variety of available trajectories. In particular, helical pattern enable the tomography above and below the ground surface, where high resolution cross-section at different heights of the trunk as well as at different depths of the subsurface can be achieved or performed. And the next step is enhancing the performance of such technique. And in particular, one of the efficient trajectories types for implementing this SAR tomography with drone-borne SARs is spiral trajectories. I will show you later on the geometry. But it is well known that cylindrical or spiral geometry of an antenna array suffers of a higher level of antenna part side lobes compared to those of linear antenna array. It is well known numbers in cylindrical geometry is minus 80 dB, the first side lobe, versus minus 13.5 dBs in rectangular arrays. And this brings degradation in SAR image quality and also may produce false alarm, which requires elaboration of new methods to suppression of these side lobes in the voxels. I have to note that when we have been working in ground SAR in my laboratory, we also try to use different geometry of scanning, and we found very poor quality of image if apply cylindrical geometry or spiral geometry. That's why we ended up on the linear antenna array. And we suggested to use a random distribution of array elements or antennas to suppress antenna part and side lobes, and basically relying on the physical reason of side lobes appearance. The interference of signals received by different elements of antenna or transmitted. So this is the phenomenon, electromagnetic phenomenon. And then we generalize this approach on the SAR image generation algorithms and illustrate its efficiency in suppression of voxel. Voxel means a pixel, three-dimensional pixel. Side lobe. When applying random distribution of data acquisition points, DAP, DAP, of a spiral drone-based SAR. And we analyze theoretically the point spread function when using the back projection algorithm for synthetic aperture radar image formation, and have demonstrated the side lobes suppression in the certain cases up to minus 30 dB. This is the radar's drone-borne SAR. These three different antennas for three different wavelength bands, L band, C band, and P band. This is amazing. The oxycopter enables to perform the high resolution imaging. Now, first we decided to estimate antenna array pattern in the far field zone using a textbook's equations. And we have to estimate the phase of the wave received by M's array element, this theta sub M. This is straightforward geometrical equations. If will be questions, I will explain later on. What is important for us, we have to study and we use the normalized antenna array factor or antenna array. And this is extremely simple equation. It has a formula too. In this equation, we also can take into account the magnitude and the phase of the weighting, if needed, weighting procedure or antenna beam pattern for individual elements. But here we suppose this is isotropic antenna pattern, and then we use this is actually the phase summation of the equal amplitude signals with different phase. Then use also normalized antenna array factor. We did several simulations. The first, just illustration of a geometry which we use. It's in reality this is spiral motion from shorter radius to widening radius with a decrease of altitude. This is like an illustration 3. Such trajectories were shown. And then we did the estimation of this antenna pattern. This is geometry was taken with 150 meters in radius and 1001 antennas or data acquisition points. And this parameter L, I will explain later on what it is, characterizing randomnesses in data acquisition points. This is regular circle, and we see antenna pattern in elevation. In azimuth, we suppose that it is omnidirectional, and in elevation, we have the main lobe formation and series of side lobes. And the first side lobe is about minus 80 dBs. So we took 20,000 elevation angles. Why? Because we wanted to, with all fine structures of antenna beam pattern. Now we have wanted to randomize antenna arrays elements, positions. And we introduced the radius in cylindrical coordinates. This is non-disturbed regular radius. And this L is number of wavelengths multiplied on the random deviation of the trajectory radius in the horizontal plane. And we use the standard MATLAB random signal generator for that. Is this equation? I don't see it, but you have to see it. And NAZ, this is the number of dots in azimuth. Now we introduce this parameter L to the value of 1, departure 1 wavelengths. So this is such it looks like the set of these data acquisition points, and this is the antenna part. We can see there's a little bit lower the first side lobe, but not that much. Then we have to increase up to 10 lambda this parameter characterizing the deviation from the regular trajectory. And we can see that up to 26 dBs, not the first but the third, it's a little bit higher, others. Oh, this is already not bad result. So surprisingly, sorry. Then we did extreme 100 lambda, and with 100 lambda again we have about 27 dBs the side lobe level, and also we observe narrowing of the main beam. The main beam is here, amplitude, and this related to increasing the efficient dimensions, the antenna array. Then we decided to estimate, we need to point spread function for SAR back projection algorithm and random set of the data acquisition points. So first we estimated angular side lobes of point spread function, and we choose the coordinates 10, 0, 0 meters using the back projection algorithm. We put this point like scatterer, and then Gaussian random distribution of these data acquisition points in spiral drawn boron SAR with trajectory with 5 rings and 1001 numbers of the data acquisition points on the whole trajectory. This is how the trajectory looks like in the MATLAB simulation. Then this parameter L equals 0, the regular trajectories. And this is estimated antenna patterns in different Cartesian coordinates, x, the next one y, and then zeta, elevation. In elevation, the picture is very different because the distribution of the antenna pattern is different for the height, for the altitude coordinate. And here we see this minus 8 dBs side lobes. Then we did extreme 160 these coefficients of the randomnesses, and this is how trajectory the behavior is random, and it's very high deviation departure of the random of the regular trajectory. The results are not as nice as for antenna pattern simulation, but still we have, we observe the widening, and we observe minus 15 dB, or if you like, we can minus 20 dB in both x and y coordinates, and in altitude, then results a little bit worse, but they are related to another reasons. So, of course, the work wasn't finalized, but this intermediate conclusions that we have cylindrical or spiral geometry gives us side lobes level minus 80 dB versus minus 13.5 dB in rectangular antenna array. And we suggest application of random distribution of the array elements to suppress antenna pattern side lobes, relying on the interference of signals received by different elements of antenna array. And we have shown efficiency of that approach in SAR tomography when applying random distribution of data acquisition points of the spiral drawn boron SAR. Point spread function when using the back projection algorithm has been estimated. We showed the suppression of side lobes down to 25 dBs. And that's all. Thank you for your attention, and I'm ready to answer any questions. Thank you.